Every shotgun shell you've ever held passed through a system most people never think about. A factory engineering millions of identical rounds where a single material inconsistency or missed inspection can compromise an entire production lot. Since 1869, the challenge hasn't been building one shell. It's been building millions without a single failure slipping through, and it all starts long before anything reaches the assembly line. In 1969, the first patented paper shotgun shells offered an economical alternative to heavy brass casings. By 1900, manufacturers introduced waterproof paper hulls, which minimized moisture swelling but still required slow, labor-intensive manual assembly and end-of-line quality checks. The industrial layout shifted permanently in 1958 with the introduction of high-density polyethylene hulls and subsequent one-piece plastic wads. Unlike fragile paper, polymer could be rapidly extruded, heated, stretched, and formed on a continuous loop. This material evolution reshaped factory floor engineering, replacing isolated manual workstations with high-speed mechanized assembly lines that operate around the clock. Today, standardized polymer components allow synchronized automated machinery to feed, load, and crimp millions of consistent shells, converting a series of disconnected manual tasks into a single, continuous, and highly integrated industrial system. Multiple raw material streams enter the facility simultaneously, requiring strict organization by material type, physical condition, and immediate production demands. To manage this bulk volume, large bins and conical hoppers house the incoming plastic pellets, metal rims, and lead shot before any manufacturing begins. From these storage vessels, automated vibratory feeders and mass flow screw concepts regulate the bulk discharge, shifting raw materials steadily into the main production pipeline. Factory logistics personnel monitor these systems to maintain controlled availability, ensuring the automated line is constantly supplied rather than manually handling individual parts. An engineering principle dictates this entire layout. A production line cannot be faster than the material handling system feeding it. Maintaining a highly consistent discharge prevents upstream feeding interruptions from propagating downstream to the tooling. Even minor variations at the intake point can lead to machinery starvation, material accumulation, physical contamination, or component confusion. By stabilizing this initial flow, the factory secures the continuous, uninterrupted movement of materials required by the high-speed assembly cells located further down the line. Integrating safety directly into the physical layout of the factory floor establishes a series of defined operational boundaries. Restricted work zones partition standard manufacturing areas from high-hazard cells where propellant and primers are handled. Along the assembly line, interlocked physical guards enclose high-speed rotary drums and indexing tables. If an operator opens a protective gate, safety interlocks instantly de-energize the drive motors to prevent mechanical impact. Beneath the machinery, specialized dust collection enclosures and regular housekeeping routines prevent the accumulation of fine particulates. Workers within these boundaries follow strict protective protocols, utilizing static grounded footwear, conductive flooring, and non-sparking tools. Even the internal transit of finished goods is confined to marked, grounded paths. This structured environment ensures that the high-volume movement of components remains entirely controlled, treating worker protection not as an afterthought, but as a fundamental requirement for continuous, predictable production. The main assembly floor operates as a series of linked, highly synchronized cells where mechanical movement coordinates with digital tracking. Forming equipment first establishes the baseline geometry of the polymer hull, shaping the raw plastic into repeatable profiles. Once shaped, the hulls move through a series of operations using precise indexing systems. These systems physically advance each unit through a controlled sequence of workstations, pausing long enough for specific operations to occur before moving forward. To keep different machine cycles from interfering with one another, a network of conveyors and small physical buffers separates neighboring steps. This buffer system allows upstream processes to continue briefly, even if a downstream machine temporarily pauses. Throughout this continuous flow, presence and position sensors, using photoelectric, inductive, laser, or ultrasonic methods, verify the status of every single unit on the line. These sensors send real-time data back to programmable logic controllers, or PLC systems. If a shell is misaligned or missing, the PLC instantly coordinates equipment responses and triggers system alarms to prevent mechanical damage. By coupling mechanical motion with constant digital surveillance, the production line functions not as a collection of independent machines, but as a single, unified chain of synchronized handoffs. The line supervisor coordinates the entire system from a central control interface instead of manually performing individual assembly tasks. Digital dashboards display real-time machine status and instantly communicate alarms to the operations team. When the system flags an issue, maintenance technicians and operators respond immediately to maintain equipment reliability. Rather than improvising repairs on active machinery, the team relies on authorized controlled stoppages to resolve interruptions safely. Automation provides the constant speed and physical movement needed to sustain high production volumes, but human personnel decide how to respond when the expected mechanical rhythm breaks. This structured cooperation balances high-speed manufacturing with strict physical protection for everyone on the floor. High-speed assembly lines require continuous physical evaluation to verify that every unit matches exact manufacturing specifications. Inline inspection systems evaluate each shell for proper component presence, finished form, and dimensional consistency. High-resolution cameras scan for visible surface irregularities, while integrated checkweighers and physical gauges measure finished weight and profile dimensions without slowing the line. When a measurement falls outside acceptable tolerances, automated reject mechanisms instantly divert the non-conforming unit into isolated containment bins. This immediate isolation prevents defective parts from moving further down the production sequence. Simultaneously, statistical process monitoring software analyzes real-time measurement trends to identify subtle process drift before it causes systemic manufacturing failures. While the line supervisor manages production output, a dedicated quality engineer holds the authority to stop operations. The quality engineer protects the conformity of the product rather than the speed of the line, determining when an exception requires a complete system pause. Correcting these deviations follows a strict corrective action loop, detecting the error, isolating the affected batch, investigating the root cause, executing the mechanical correction, and verifying the repair. This methodical loop ensures that high-volume production remains stable, predictable, and compliant with safety standards. Physical completion at the end of the high-speed assembly line does not constitute official product release. A completed lot remains isolated until an electronic batch record compiles all process and inspection data for a formal release review. This review assigns a definitive release, hold, or review status to ensure only conforming material moves outward. Once authorized, horizontal case packers group the finished shells into standardized containers that provide physical protection and information control. Automated systems apply labels, codes, and barcode or radio frequency identification tags, linking each shipping container directly to its specific production run. This precise labeling establishes complete traceability, connecting the finished lot back to its original raw material batches and manufacturing conditions. If a quality discrepancy is identified later, these lot records allow engineers to pinpoint the exact production group and components involved. Finally, the logistics coordinator translates this compiled manufacturing data into a usable warehouse and shipment record, officially transferring the authorized inventory into the distribution network. The warehouse operates as an active control zone rather than passive storage. Once authorized, finished cases are arranged into stable pallet loads, each assigned a specific pallet level identifier. The logistics coordinator tracks this movement from initial record creation to final outbound reconciliation. Handheld scanners log each pallet's physical transit, instantly updating location information within the Warehouse Management System, or WMS. To maintain system-level accountability, the factory's Manufacturing Execution Record System, or MES, must reconcile perfectly with the WMS, matching actual production output to available physical stock. This digital synchronization prevents inventory mismatches before shipment preparation begins. The final pressure point occurs at the loading dock. Before any load is released to the wider supply chain, an outbound verification check matches the physical pallet's barcode directly to the intended shipment record, guaranteeing complete data alignment. Ultimately, this factory floor represents more than mass production. It is a study in extreme precision at scale. As modern manufacturing pushes for even higher automation, the challenge remains unchanged, balancing absolute consistency with human oversight. What industrial systems should we explore next? Tell us below.